Oh my god, this is it. The last video that you'll hear me make for you this semester. What a long way we've come. It's been really stressful lately with all the stuff going on, and I've been having trouble sleeping. Like when I do sleep, I have weird dreams. Like last night, I dreamt that I was a muffler on a car, and I woke up so exhausted. Ha ha ha. If you can't tell, the theme of today's jokes is dreams. My mom always told me to never give up on my dreams. So I slept all weekend. One time I had a dream that the ocean was full of orange soda. It turns out it was just a fantasy. And last one, a man went to the doctor complaining and he said, "Doctor, every night I have dreams about playing soccer with donkeys." The doctor says, "Well, that's very strange, but I have just the medicine you need for that." "Well, doctor, can you wait until tomorrow to prescribe me the medicine?" "Uh, yes, but why?" said the doctor. And the man says, "'Cause tonight we play for the championships." All right. And with that, we math. So today is graphing logarithmic functions. We're wrapping up this kind of unit we've been doing over logarithms. And then there'll be one more video that Miss O'Neill will do to talk about the transformations on these. But today we're just going to introduce this. The essential question today is how are inverse functions going to help us? And so graphing logarithmic functions in itself actually turns out to be kind of tricky. If we're going to graph a function, we want to come up with points, and so usually it's nice to organize those points into a t-chart or a table or something like that. And so we think, figure out like, well, what do we want x to be, right? And we always get that choice, like, let's pick some values for x. And a lot of times we pick like positive numbers, negative numbers, and it's always nice x to be 0. And so it's like sometimes we just kind of throw numbers at it and say, hey, what if x was, 0? What if x was 1? What if x was 2? Okay, let's look at some negative numbers. What if x was -1? What if x was -2? And so we try to plug those values into the function. So f of x equals log of x, and say, well, that means that f of -2 would be log of -2, and f of -1 would be log of -1, and log of 0, and log of 1, and log of 2. And so we think, well, what's log of 1? What's log of 2? Like, what's log of -2? What does that mean? So remember that a logarithm is a question about that x, the base. So this really says, that last problem really says, log, and we say log, that means we're talking about log base 10, so that's the common logarithm of 2. So what's log base 10 of 2? What does that mean? Right, and that's, well, 10 to the what power equals 2? Well, I have no idea what 10 to the what power is 2, right? So that one's really hard to evaluate. I don't know what log of 2 is. If I say, well, what's log base 10 of 1? 10 to the what power of 10 to the what power is 1? Oh, well, I actually do know that. 10 to the 0 power is 1, so that's equal to 0. And 10 log base 10 of 0. What power? What do I have to raise 10 to get 0? And well, there's nothing I can raise 10 to get 0. That doesn't even exist. And so that's actually undefined. And log base 10 of -1, same thing. So 10 to the what power equals -1. And again, there's no numbers we can raise 10 to get -1 as an answer. So this is undefined. And it turns out that this is also undefined. So we look at, we only have one point here so far that we've could even plot, which is 1, 0. You're like, oh god, that's not, I can't make a graph out of 1 point. And if you think about, saying, continue this table, if we went all the way up to 10, like log base 10 of 10, so 10 to the what is 10? Well, that's 1 at least. We know that's equal to 1. So I have to get all the way up to 10 to get 1. And so again, I got 2 points there. It's really nothing too helpful. So, evaluating logarithms is tough, and so graphing a logarithm by itself is tough. So luckily we have some other things we can use to help us graph logarithms. And so looking at that, so what it turns out is that, graphing exponential functions is really easy. So if we do that same idea, saying, hey, let's throw those same x values at an exponential function. And that's actually really easy to do. So, 10 to the negative 2, 10 to the negative 1, 10 to the 0, 10 to the 1, 10 to the 2. Well, we know the values of all those things. So 10 squared is 100, so we get the point 2, 100. 10 to the first is 10, so we get the point 110. 10 to the 0 is 1, so we get the point 0, 1. 10 to the negative 1 is 1/10. And then 10 to the negative 2 is 1 over 10 squared, which is 1 over 100. And so we can evaluate those points all really easily. So even though they're not super easy to plot, because 2, 100 is a big point, we can find the values at least. So we got 1, 10. So at 1, it's at 10. 0, 1. Negative 1 is at 1/10. So it's way, I'm going to zoom in a little bit. So, 1/10. So it's way down here. And then negative 2 is at 1/100, which is even closer to the x-axis. Hard to get that close. And so if I look at those, we see that this is a curve. Oops. And so the curve of this line does this. Or the curve of this graph does this. And we've graphed exponential functions before. And so that graph, there's f of x equals 10 to the x. Easy to graph. Okay. And so, things we might remember about exponential functions is they have something called an asymptote. And that's that line that the graph approaches nearer and nearer to as it tends towards infinity. And so this asymptote is at 0, where it's y equals 0, since it's a horizontal line. Because there's no value of an exponent that we could ever plug in to make it equal to 0. It's going to get smaller and smaller and smaller and smaller and smaller, but never reach 0. Like 10 to the negative 1,000 still is this tiny, tiny, tiny number, but it's still bigger than 0. So that graph, just as it heads off to the left, just keeps getting closer and closer and closer to the x-axis, but never actually reaches it. But as it heads toward the right, it grows really rapidly. 10 to the first is 10, 10 to the second is 100, 10 to the third is 1,000. Like, those values are increasing incredibly fast. So, one thing, right? It's easy to graph an exponential function. And the other thing that makes this a lot easier is the inverse functions. Way back in Unit 2, you guys learned about graphing inverse functions and what inverse functions, like how to find inverse functions are. And we've been talking about this unit, how that exponentials, so if I just say, y equals 10 to the x, and logarithms are inverses, so that x would equal log base 10 of y. Those are inverse functions. And so if you notice what happened here, and this is again something we learned back in Unit 2, is that where the y was is now where the x is for our new function, and where the x was, like normally the thing we plug in is our x, that's what the y is now. What that told us, what that shows us here, and what we learned back in Unit 2 was that to graph graph an inverse function, all we have to do is take our x values and our y values and switch them. So that means all of my x values will now become my y values. So this will now be negative 2, that will be negative 1, that will be 0, that will be 1, that will be 2. And then all of my y values will now become my x values. So 1/100th, 1/10th, 1, 10, 100. So this would be my new x, but it came from the y's. And then this here we call that maybe like g of x would be log of x. So, but those are our y values now. So if I try to graph those, oops, get rid of that. Actually, let's get rid of it. So if I try to graph those, so 1/100th, -2. So that's going to be really close to the x-axis. But down here, -2. And then -1/10th, -1, again, really close to the x-axis, but here at -1. And then 1, 0. And then 10, 1, way out here. So there's that 10, 1 we saw, and that 1, 0. So those are those 2 points that we had earlier on the last slide, but weren't too helpful. But now we can kind of see what's happening. And so this curve does this. And so we talked about the asymptote for the exponential curve was the line y equals 0, that x-axis. Well, if that everything is flipping, right, all of our x values became y values, the asymptote also flips. It's pretty cool. So here's our new asymptote for our new function. And it turns out it's the line x equals 0. So the asymptote for a logarithm is vertical, whereas the asymptote for a exponential function was horizontal. Group this stuff. So there is our logarithmic function. We can see that it has a vertical asymptote at 0. And we use, to graph a logarithm, we are going to use the exponential function that it's related to in order to do that. So we're going to be able to evaluate an exponential and then use what we know about inverses to find the points we actually want, and then we'll plot that graph. So what you guys are going to be doing is drawing this graph here. You won't have to draw this graph here. So as we'll just do a couple examples, kind of show you how quick it goes. There are a couple of things that I want to make sure we find the asymptote, and we're also going to find the domain, the range of our logarithmic function. So again, we're going to find these points, but we're not actually going to plot them. We're really after these points. So we just use these as kind of a tool to find these. Okay. So our goal is to graph log base 2 of x. In order to do that, we're going to have to use 2 to the x. Okay. So just notice how the base of the logarithm is the same as the base of our exponential. We're always going to use those same x values that we were using before. So just from -2 to 2. There are certainly other values that can give us helpful numbers, but this is just a good place to start. So 2 to the -2, 2 to the -1, 2 to the 0, 2 to the first, 2 squared. Of course, that's 4. So that means that that's my y value, so my x value over here is going to be 4. And since my x value here was 2, that means that's my y value now. 2 to the first is 2, so that's my new x value here, and then my x value was 1, so now my y value is 1. 2 to the 0 is equal to 1, so that's my new x value. And my x value was 0, so that means that's my new y value. 2 to the -1 is 1 over 2, so that's my new x value. My y value is -1. And 2 to the -2 is 1 over 2 squared, which is 1 over 4. So that's my new x value. And my y value must be -2. So always just taking our x value, making it our new y value, taking our y value, making it our new x value. It's just easy switch. All right, so I'm going to plot these points here. So 1/4, -2, right up next to that x-axis. 1/2, -1, 0, 1, 0, 2, 1, and then 4, 2. So as you notice here on that left side of the graph, how it's getting closer and closer to that y-axis. So again, that's our asymptote. It's always good to draw that in with dashed line. Sometimes it's hard for you when you're using pencils and stuff like that, but it's a good idea to draw that in and then label it. So that'd be x equals 0. Vertical asymptotes are always those x lines. I'm finished drawing my curve here. So it's going to go down forever. Just kind of run parallel to that y-axis. It's going to slowly curve off to the right. What you don't want to see it doing is like shooting up or going flat or going down. So it should be a slow growth to the right. Okay. So don't do any of those, like where I usually say it like bells out. So slow growth off to the right. So there's our curve, there's our asymptote, and then the domain and the range. So remember, domain is those x values. So we look at our left side first, and we move along, and we see that we don't hit the graph until it's just past 0, and then it goes right forever. Okay, and what we noticed about all of those x values that we were using is that they're getting closer and closer to 0, but they're always going to be bigger than 0, but they're never going to reach 0. So our domain is that x is greater than 0. Our range is those y values, so we start on the low side. So we start on the bottom, we notice that that lowest point on the graph is an arrow pointing down, so the graph's going to go down forever. And we look at that high side of the graph, and the graph is also, very slowly, but it's going up forever. So graph goes down forever, it also goes up forever. That means that this is our all real numbers. So we can use that symbol for all real numbers, or you can write out all real numbers. So find the domain range, pretty simple for this type of function. All right, I'll do that one more time with you, but this is really the gist of the lesson here. Okay, so we have this function that we want to graph, which is the log base 1/5 of x. And so in order to do that, we're going to raise 1/5 to the x power. We're going to find those values. So I'm going to start with those. -2, -1, 0, 1, 2. So some positives, some negatives. So that means 1/5 squared, 1/5 to the first, 1/5 to the 0, 1/5 to the -1, and 1/5 to the -2. Well, of course, 1/5 to the 0 is 1, and 1/5 to the first power is 1/5, and 1/5 squared, so 1/5 times 1/5. So that'd be 1 times 1 over 5 times 5. So 1/25. Remember what happens with negative exponents? When we take a negative exponent, it gives us a fraction. So if we have a fraction that has a negative exponent, it turns back into, takes that fraction and flips it upside down, so it turns actually into a whole number. So 1/5 to -1 is actually just equal to 5. And then 1/5 to -2, so it flips it, there it goes the negative, and then we get 5 squared, so 1/5 to -2 is actually 25. So we take those y values, and they become our x values. We take those x values, and they become our y values. So 5, -1, 1, 0, 1/5, 1, and 1/25, 2. So there are the points I'm going to plot. Of course, I can't plot 25, -2, but I can't plot 5, -1, 1, 0, and then 1/5, 1. So that's right over there, close to the x-axis or y-axis, and then 1/25, 2, or even closer to the y-axis, but again, not really possible. So again, we see that those x values are getting closer and closer and closer to 0, but they're never going to reach 0. Same thing as look at that graph, it's getting closer and closer to that y-axis, but it's never going to reach it. So there's our asymptote. So at x equals 0. So if you haven't noticed the pattern there, you certainly should. There's for a log without any transformations like shifts, anything like that, your asymptote will always be at x equals 0. And draw on that curve. So this one goes up along the y-axis and then curves down and to the right. Oops, not very happy about that. And slowly going down to the right. It should not do this, should not come back up, should not be flat. Okay. So there's our curve, there's our asymptote, and then domain and range. So as we look at the left side of the graph, we do not hit the graph until it gets just beyond 0. So again, and then all those x values get bigger and bigger and bigger. So all of our x values are bigger than 0. So x is greater than 0. And we look at that graph again for the range, so start on the bottom. Notice that the very lowest point is an arrow that's going to slowly head down forever. Very highest point is an arrow that's going to point up forever. So again, all real numbers because they're going up and down forever. Okay. If you don't notice the pattern there, you certainly should. The domain will always be bigger than something, which is going to relate to asymptote. When we start seeing shifts, which is what Miss O'Neill will talk to you about, she'll talk to you about the shifts and the stretches and the reflections and stuff like that, that will change the asymptote and the domain. You know, if the range is everything, well, we can't change everything. Even if I multiply everything by 2, it's still everything. If I shift everything up 4, it's still everything. Like, we can't change everything. So the range for a logarithmic function will always be all real numbers. So there will be some changes to your domain depending on how things shift, but this will always stay all real numbers. So there is graphing logarithmic functions, the basic ones. You guys will have a worksheet to do for this. So again, just print it out, or I had quite a few students that just drew it by hand. It's just going to be 4 graphs. So so write those tables down. We will expect to see the tables, and label your asymptote, and just like I did here, and find the domain and the range just like I did here, and you'll be doing good. And since this is the last video, I hope you guys have a good rest of the semester for all your classes, and just have a good summer, and you stay healthy, and you come back in the fall, and hopefully things are as normal as they possibly can be. Yeah, really appreciated meeting a lot of you guys over the year, and hope to see you in the hallways. So take care.